Hello, my name is Galvis, and during this presentation I will be talking about linear time suffix tree construction, or at least that's going to be the main focus of this presentation. So let's take a look at the contents that I'll be going over. So first of all, I'll be mentioning the longest common substring problem, or LCS problem. I'll be discussing some of the properties, and after that I'll be going over some background definitions that we need to first understand in order to see in depth how to construct suffix trees in linear time. So things like what is a suffix tree and edge labels, path labels, things like that. After that, we're going to get into the actual linear time algorithm that is used to construct these suffix trees, which is going to be there are many ways to build these trees, but I'll be focusing on the Ukkonen's algorithm. We'll also going to see a visualization of how this algorithm works. So there will be a step-by-step process that I'll be talking about later on. And then finally, I'll be going over some useful applications that we can use suffix trees on. So getting started, let's go ahead and talk about the longest common substring problem. And the problem basically goes like this. Given two strings, x and y, of total length n, over a constant sized alphabet of size m, we are asked to compute the longest common substring in linear time, so in O of n time. This can be easily solved in O of n squared time by implementing dynamic programming. However, the time complexity for this can be improved to linear time by using suffix trees, which can be built in linear time by implementing Ukkonen's algorithm. So as an example, we have two strings, x and y. String x is made up of the characters AC, A, BC, and then string y is made up of characters BA, BCA, yeah. And then we can see that the longest common substring is ABC, or the string that is made up of the characters ABC, which has a length of 3. And then we can see that other common substrings include the characters A, the characters B, C, AB, BC, so on and so forth. So now that I've talked about this problem, let's go ahead and talk about some background definitions. And after I go over these definitions and I explain the algorithm, we're going to go back to the LCS problem and we're going to see how to solve it using Ukkonen's algorithm. So let's start by explaining what a suffix tree is. A suffix tree is just a tree data structure that contains all the suffixes of a given input as keys and positions to their corresponding values. So if we want to formally define it, excuse me, we can say that for a suffix tree S, we can say that it has exactly n leaves, starting from 1 all the way to n. It has internal nodes, and those nodes have at least 2 children except the root. So every node that you see in a suffix tree is going to have two edges coming out of it, unless it's the root. Edges can be labeled with a non-empty substring of S. Also, no edges starting from a node can have labels that begin with the same character. And then concatenating all the labels that result from a path starting at the root to leave I spell out the suffix in the string from I to n. So 3 more definitions here. First one is the label of a path is the concatenation of all substrings that make up the path, starting from the root and ending at the node. And then we have the string depth, which is the number of characters in the node's label. And we're also going to see a picture of how all this is how all this makes sense, which is going to be better to understand. And then lastly, a path that ends in the middle of an edge splits the label at a designated point, and then the label of that path is defined as the concatenation with the character on the edge down to the designated split point. So now we see an actual suffix tree. We see how it looks like. So for this particular example, we have the suffix tree for the string ABC ABX. And so going over back to this first definition, we see the label of a path. So in this case, we're going to be taking a look at this edge over here. And so we see that CABX is the label of a path from where the root ending at the node with index 3. So we start at the root and we end up at index 3, assuming that our indexes start at 1. And so we see that the label is CABX. That's because those are the characters that make up that path. And so we can see that node with index 3 has a string depth of 4 characters, because that's the number of characters that we encounter on this specific branch of the tree or edge. And then the path from the root to W ends in the middle of the edge. So the label of W is defined as AB. So again, we start at the root. We see that W is a node that ends in the middle of an edge. Therefore, the label of the path is AB, because those are the characters that compose of that path. So to avoid matching a suffix with the prefix of a different suffix in a given string, there is this thing that we can do, which is to use a unique character or some character that is, or some symbol that is outside of the string's alphabet. In this case, we're going to be using the $sign as the termination symbol. And so this termination symbol allows for the opportunity to create unique leaves where the last character in X does not appear repeatedly in the string. So for example, we have a string X. It's made up of A, C, B, A, C, and then the $sign to mark the termination symbol, or sorry, to mark the termination of a unique string. And so by doing this, we can now say that AC is not a prefix of the suffix ACBAC with the $sign. And therefore, it is a unique leaf. Now, with these suffix trees, we can easily determine the number of occurrences of a pattern in a string. And so we see that the number of occurrences of a pattern in a string is equal to the number of leaves reached after searching for the pattern, obviously starting at the indices from the search. And this can be done in O of n plus m, where n represents the length of the string and m represents the number of occurrences. So for example, we have this suffix tree, and we have, so the overall string is ABX, ABY, and ABZ. And if we want to search for the number of occurrences for AB, we can look at the index at which these happen. So for example, we have the first occurrence, which starts at index 1, then we move up to index 4, we see another occurrence, then we move up to index 7 and we see another occurrence. So therefore, the index 1, 4, and 7 are able to tell us that there's only 3 occurrences of this particular pattern within the string. And so we can determine that the leaves match to indices of the characters, and so therefore AB has 3 occurrences. Now we can get into we can get into the actual algorithm, which is to build a suffix tree in linear time. And this can be done by implementing the Ukkonen's algorithm, which was proposed by Esko Ukkonen in 1995. That's him in this picture down below. And then what this algorithm does, it implements the use of implicit suffix trees, also a set of steps, extensions that we're going to be making to a tree, and following these extensions, and then these extensions have to be followed by a set of rules that we're going to be talking about in a minute. And so the overall time complexity for this algorithm is linear, so O of n, for a constant sized alphabet. So let's talk about implicit suffix trees. Since I mentioned them earlier, we need to understand what they are. So implicit suffix trees, all they do is they remove the $sign, or in this case the $sign, but it's removing the termination symbol from the edge labels at a suffix tree. It also removes any edge that has no label in a suffix tree, and then it removes any node that does not have at least 2 children in a suffix tree, and we're gonna see how that comes into play. So for example, we have this first suffix tree for the string xabxa, and then we have the termination symbol. So first we said that we need to remove the termination character. So this is the original suffix tree. We now move to the second picture, which is by removing all the termination characters. So we see that it no longer has them. Then we remove the empty edges, or the edges that have no labels. So for example, this from this node to index 4, from this node to index 5, and then from this node to index 6, we see that all those edges are empty. Therefore we simply remove them. So down in this picture we have removed them, and now the last thing to do is to remove the nodes that have less than 2 children. So we see that there are these 2 nodes in the middle of the path, and they only have 1 children. Therefore we need to remove them. So we remove them, and then we simply unify or concatenate both paths that result from the removal of those nodes. And so we end up with a implicit suffix tree for this particular string. Some important observations to take in mind or take into account while applying this algorithm is that first, implicit suffix trees, or an implicit suffix tree s of I, is built for each of the prefix of s with a length n, and then s of 1, so a suffix tree s of 1 is built beginning at the first character all the way up to s of n, which represents the nth character. And then we also see that the implicit suffix tree s of I plus 1 is built upon implicit suffix tree of s of I. So what I'm basically saying is that we start with an implicit tree, and we're going to keep building upon it until eventually we have finished a completed suffix tree. So we're just going to keep on building upon the same implicit suffix tree over and over until we finish all the iterations of the characters in the string. We see that the algorithm is divided into n phases, and one phase is for each of the character with length n. And each phase can also be divided into I+1 extensions for each of the I+1 suffixes. So we have phases, and then these phases have subphases, if you want to call them that. And then at each phase, we're going to see whether if we need to extend the suffix tree or not. And if we do, we need to follow 3 main rules, as I mentioned before. And now we're going to take a look at what those 3 rules are. So the rules of extension, I'll just read these 2 lines, and then I'll explain what it means. We have let s from j to I equals t be a suffix of s from I to j. We have t is extended in the current tree in extension j to make sure the suffix is in the tree. So all this is saying is we have a path t, and we're going to determine whether if it needs to be extended or not, and if it does, we're going to see which rule applies for this extension. So going over the first rule, we have if the path t ends at a leaf, the character s of I plus 1, so the next character, is going to be added to the end of the label on that edge. And that's all we do. After we're done that, if there's nothing else to do, then we proceed with the next character. Now for the second rule, if no path from end of t starts with a character s of I plus 1, but at least one label path continues from the end of t, then a new leaf edge starting from the end of the path, which is t, is created, and then we label it s of I plus 1. So we label it the next character. And then a new node will also be created if t ends inside an edge. And so if t ends in an edge, there's this thing that we need to do, which is a split, and we're going to see how that comes into play. And so the leaf at the end of the new leaf edge is giving a number j, or this number is to indicate the index that we're at. And then the last rule states that if a path from end of t starts with a character s of I plus 1s, it means that the concatenated string is already in the tree. Therefore, we don't have to worry about it. We can simply move on with the algorithm. So now that we have taken a look at those three rules, we also need to take a look at one more thing before we actually get into the algorithm, which is a suffix link. So given a string a and b, where a represents a single character and b represents a substring, or it could be non-empty, for any internal node v with a path label a and b, if there's another node s of v having a path label a, then the pointer from v to s of v is called a suffix link. So in this particular case, we have this node v, and it's pointing to s of v, and this link over here is called a suffix link. And so in this particular case, a is just a single character, it's just the character a. And now, there's one more important thing to consider, which is active and endpoints, and these are key to understand at what step are we at in the throughout the algorithm. So the tree maintains a canonical reference pair to the state or node, which is, state and node refer to the same thing, which represents the longest suffix from the previous step that occurred at least twice, and this is called the active point. And then after step I, we traverse the path from the active point to add more nodes if needed until we reach an endpoint. And once we reach an endpoint, this means we've reached a state that already has the character at index I. Now that I've gone over the main principles of Ukkonen's algorithm, we can now visualize how it all comes into play. And so for this specific example, I'll be going over the construction of a suffix tree for the string a b a a b c a b. And so, like I said before, it's going to be divided into a series of steps, and we're going to perform different actions based on the rules that I have previously mentioned. So we begin at step number 1, which is we know that the active point is at the root because this is our first character, we have nothing else. So we take a look at the first character, which is a, and we see that the root doesn't have a transition or an edge. Transition or edge means the same thing with the character a, so we add one, and therefore this results into a new node, which is node with index 1, and that's all we do. We just add a new transition and a new node, and we move on to the next character. And so since there's nothing else left to do from step 1, we can now move to the second character, and we see that we have a new active point, which is the same that we had at the beginning when we inserted a. So we basically repeat the same exact process that we did for a, but this time we do it for b because we're looking at the second character, which is the b character, and we add b to each of the path labels, since we're using a variable to keep track of the length of the process string as the second index. This is on the edges that lead up to leaves, and so we extend the path label, and that's all we do, and we can move on to the next character. So now we're looking at the character a, And so what we have to do here is we add them to the path labels, and we notice that our active point has already an edge with the character A, therefore we don't need to create a new node. And so whenever we later on in this string we're going to have to make a split, and every time we have to make a split we're going to have to see how suffix links come into play, but this time we're just simply extending the edge labels with the character A. So and we're also not creating any new nodes, and so at this point the active point and the endpoints are the same, and so we move on to the next character. On step number 4, this is where the first split occurs, and we'll see how it happens and how the first suffix link is created. So based on our previous endpoint, we know that our active point is located at the root, and we're looking for another A because we're currently at the 4th character, which is an A. So we see that the edge that we're currently sitting at continues with a B. Therefore, we need to make a split, and this split is going to create a new node, which is the node with index 3, and we have to insert it between the root and the index, or the node with index 1. So here we have 3, and we have inserted it in between these two nodes. And so after this, we now have to add the transition with the letter A from node 3 to the new node, and then we can go back to the root, and we see that there's already a transition with the character A starting at the root, which means that we have reached an endpoint. And so we since we made a split earlier, we now have to create a suffix link between the node 3 and the root. And after this, that's all we do for this step, and we proceed on with the next character. So on step number 5, we now are looking at the character B, and we see that the current active point is located at node 3, and so we see that there already is a transition with the character B from the active point, which means that the active point and the endpoint are the same, and when this happens, there's nothing else left to do. We simply move on to the next character. So now we can move on to step number 6, which is to take a look at the 6th character in the string, which is a C. And so currently our new active point is located at 3, transition B, and so we see that transition does not continue with the current character that we're looking at, which is the character C, and therefore we need to make a split. That split ends up creating 2 more nodes, which are 5 and 6, and so we're gonna keep track of 5 because we're gonna use it for a suffix link, and I'm gonna explain how that happens in a bit. But before we do that, we see that there needs to be a split. So if I go back, we see that we see that there needs to be a split between this B and AAB. So over here, we make that split, and that's to add the suffix BC. And so we can also see that we need to create a new node, which is node 7. So we can create the suffix link from 5 to 7, and we go back to the root. We see that the root has no transition for the character C, so we have to add one, and then we end up creating a new node, which is number 9. And then since node 7 was the last internal node created, then we create a suffix link from 7 to the root, and then we arrive at a new endpoint. And after this, there's nothing left to be done, and so we can proceed with the next character. So on step number 7, we are looking at one of the last characters, which is letter A. So currently our active point is at the root, and we see that we're looking for the character A, which already has a transition. And so since it already has a transition, the active point and the endpoint remain the same, and therefore we don't need to make any changes, and we simply move on to the next character. So now we are at step number 8, and this is the last character in the string before the termination symbol, and this character is a B. And so we see that the node 3 has a transition with B, and this means that our active points and endpoints are the same because we don't have to do anything else. And so this is basically repeating the same process that I repeated in step number 7. It's the same thing for step number 8. And we can move on to the last piece of the string, which is the termination symbol. So since there are no characters left to be read other than the termination symbol, and we know that this is a unique character, or a character outside the string's alphabet, we have to follow the suffix links from the active point and create new nodes until we arrive at an endpoint that is located at the root. And so we can see in this suffix tree that we have so far, we add all the termination symbols where we need to, including the new nodes. And then after all the termination symbols have been added to their corresponding places, we can now say that the suffix tree is complete, and the termination symbol ensures for an explicit leaf for each suffix. So now that we have seen visually how the algorithm works, we can go back to the LCS problem. And so like I said before, it just consists of 2 strings, and we are asked to compute the longest common substring. And so the way we solve this by using suffix trees or by using the Ukkonen's algorithm, is by implementing generalized suffix trees. And what generalized suffix trees are, they basically consist of trees where every leaf corresponds to a suffix from one of the 2 strings, so either string A or string X or string Y, or in both of them. And then all the internal nodes are marked whenever there is a leaf that corresponds to a suffix from the string X or Y. And then we concatenate all the edges that make the longest path from all the marked internal nodes, and the result is going to be the longest common substring. And that's basically how we use generalized suffix trees to solve this problem. And this problem amounts to a total runtime of O of n, where n is the size of the input string, and then we can determine that the maximum number of nodes cannot be higher depth than n, and so we can conclude that the total amount of node skips is bounded by n, and therefore the total time complexity of this algorithm is O of n. And so lastly, I wanted to mention a few other applications that suffix trees can be used for. One of them is bioinformatics. This obviously we can implement Ukkonen's algorithm to get linear time results. And so one of the things that you can do in bioinformatics is to search for patterns in DNA or protein sequences, and you can expand DNA sequences for DNA contamination research, and then it can also be used on genome scale projects. And then one other application besides bioinformatics is data compression, also done in linear time. One of the compression algorithms currently known as the LZSS implements suffix trees. And then it basically is a dictionary coding technique that replaces a string of symbols with a reference to a dictionary location of the same string. And so that would be the last thing that I was going to go over. And we have seen how the algorithm works, all the principles, and how to solve the LCS problem. So that's pretty much it for this presentation. I hope you enjoyed, and thank you for watching.